So before we start anything, let me just recap on what we had done on last day's class. So if you remember on last day's class, I have we have actually done a particular modulation scheme, which is basically I would say a refinement to a modulation, and that was DSB Sc, double sideband suppressed carrier, in which the principle was to minimize the carrier, to nullify the carrier by some means, so that the carrier which doesn't contain any information. By the way, I'm not sharing anything, I'm not showing anything. That's why for the time being, I'm just telling you. Okay, so don't worry, don't get worried. Already we have discussed this. So we have seen that since the carrier is not transmitting any useful information, all right, so we can make sure that we have a scenario that we can only transmit the upper sideband or the lower sideband of the spectrum, because in both the cases, Fc plus Fm or Fc minus Fm, the information M, that is Fm, the modulating signal, is captured in those USB and or the LSB. And we have also found out different techniques and methods. For example, the balance modulator, we have found that to be interesting. And also we have also observed something called as coherent detection in the part of the detection part, where there will be a local oscillator or a local carrier which will get multiplied to the incoming signal, and from there we will get a scaled version of the input signal. And also we have observed that there are problems associated with DSB-SC. One of the problem is that if you consider the synchronous detection, the phase and the frequency of the carrier should be exactly matching to that of the transmitted signal. Because otherwise, if there exists a phase error or a frequency error, definitely there will be chances that at different phases, particularly, you might observe that there might be an amplitude reduction or even diminished to zero, which we observed that when phi was equal to 0, when the phase was equal to 0, we were getting some value. When phi was equal to 90, we were getting some other value. So like that, so inconsistency in the output will be observed. Okay, and also we have found out the frequency error also has an issue, that the upper and the lower sideband might overlap amongst themselves because the frequency deviation has happened. And in that aspect, we might use a synchronizer, which actually takes care of the frequency and the phase mechanism or the requirement, whatever it is, and based on that, it goes on tuning the local oscillator as such. But even if we are doing that, there will be some kind of a distortion that will come in. Okay, so because the distortion is a very common phenomena that happens with any analog signals for that matter. We are dealing with all the analog signals, so that will be still there, but at least some minimization is possible. Now, keeping this in mind, let us quickly venture now towards the new topic. Now I'll start sharing actually, and that is called as the SSB-SC. Okay, so let's see what exactly is SSB-SC. All right, so the term that we are looking at is called as single sideband suppressed carrier. Okay, and in short, we call it that SSB-SC. Just like DSB-SC we had, here we have SSB-SC. So from the term itself, I think all of you at least can guess that in this case, instead of sending both upper and the lower sideband, we might only send the single sideband for our purpose. So what I mean is that in case of single sideband, the name actually comes in because we are going to transmit only USB or LSB. Okay, so either of the one we are going to send. Now, why we are doing that? Because if you remember in the coming up to SSB, when we discussed the DSB-SC, there also we have discussed that both the sideband, upper and the lower sideband, they carry the information. And as far as the symmetry is concerned, if you remember the diagram, I'll just try to quickly draw the diagram, that if suppose this is the spectrum that we are talking about, okay, and this is suppose a minus FM and this is plus FM, something like this. Okay, if this is the scenario that we are looking at, So your upper and the lower sideband will be something like somewhere over here. Okay, and this will be like something of this nature. Just approximately I'm drawing. So the observation is that this portion and this portion that you are looking at, both are symmetrical in nature. So ideally, if you are sending the upper sideband, which is basically this part, because this is FC plus FM. Okay, and this part is FC minus FM. All right, and this is also minus FC plus FM, and this is minus FC minus FM. So like this, the structure was in DSBSC also. Now the shaded portion that you are looking at, okay, the red shade that you are looking at, these are basically the USB that we are talking about. That is the only part. Okay. Now in DSB, we are sending all these two. So if I colored this as green, so both this red and green shaded region, okay, both of this. So this is my LSB. Okay, suppose I mark it for our convenience LSB1. This is my LSB2. Okay, and I'll put this as USB1 and USB2 just for our reference, nothing more than that. But this LSB2 or USB2, if you neglect that, basically what we are doing in DSB is that we are sending only both the USB1 and LSB1 together. But in SSB, what we are trying to do, we will only send the LSB or the USB. Okay, so that is the basic advantage. I'll just show you one diagram if at all that helps you. So please look into this particular diagram. This is the formal diagram that we are looking at. Okay, so if you closely observe that this is till the spectrum of DSBSC. So very quickly we can understand that if I can generate DSBSC and then if I send it through some kind of a filter, that will only allow the upper sideband. That basically is the output of an SSB signal. What I mean is, again, just to reiterate once again, because this is the only thing that you have to understand. So DSBSC is generating, okay, so I'll put it this way. So AM is there, which is with carrier, and so it will have carrier plus 2 sidebands. Okay, this is just a briefing of it. Okay, now from AM to DSBSC, when we are reaching here, we are making sure that there is only double sidebands. All right, now from DSBSC we are reaching to SSBSC, where we are considering only one side. Got it? So this is how we are trying to observe. You can see the shaded portion is what we are only want. So what we would do, that if the DSB-SC signal generation we know, suppose the balance modulator and everything is already known to us. So that signal, if it goes to some kind of a filter, okay, that makes sure that it is tuned to any particular frequency, the upper or the lower band, whichever you want. Okay, that will be the SSB signal. If you observe here, this one only USB if I want, and this diagram is showing only LSB if I want. So by that what I achieve is that you can observe the bandwidth now, the signal which is transmitted, okay, is now FC, okay, plus W. This is this point minus FC. So basically the bandwidth is now around W. If W is the bandwidth that we are talking about here, so you can observe that there is a bandwidth saving that also is observed. So what we are claiming with SSB, that first the power part is definitely, power efficiency is definitely improved, because as we have already proved in DSB-SC that using DSB-SC we are attaining amount of improvement 66 to 67% improvement, because we are suppressing the carrier. So that was already there in DSB-SC. Now we are even suppressing another carrier from or a subcarrier from our observation. So definitely there will be a boost up in the power efficiency. So that is one advantage. Okay. Second advantage that we are looking. I hope everyone is clear with this. Let me reiterate once again. What we are looking at is a power efficiency factor. If you remember in last class when we discussed the DSB-SC, one of the primary factor of DSB-SC was that we want to improve the power efficiency. And since we were reducing or we are suppressing the carrier, we were obtaining around 66% of improvement, given that M was equal to 1. All right, so that is the maximum efficiency that we were obtaining. Now, in case of SSB, what is happening that since we are reducing another sideband on top of it, carrier anyway is suppressed. Now, one of the band is also suppressed, so that definitely will improve the power efficiency. So that is one of the biggest advantage of side single SSB. Along with that, what is happening that we are also in the process improving the bandwidth efficiency too. Because in DSB, if you remember, the bandwidth was still the same. If you check in this diagram as well, the bandwidth is like this. Okay, because you're sending both the upper and the lower one. So here the bandwidth was FC plus W. Okay, suppose if with respect to this diagram, minus FC and minus W like this. So it comes around 2W. So here, if you observe that in SSB, the value is coming as small w, so the bandwidth is also reduced. And as we know that bandwidth is very expensive, and bandwidth is the less bandwidth any signal takes or any kind of process that will take is always advantageous. All right, so these are the major contribution of SSB signal. And also here in this particular left hand side diagram, I have briefly told you that how we can easily generate an SSB signal for that matter. Please tell me if you have any doubt in this aspect of it so that I can repeat it if you want. Anyone having any doubt with respect to this? Because this diagram, I think will be very clear to you what is the meaning and how we are achieving it. Okay, and these are the two major factors. Please don't forget about this too. Okay, and how we are achieving it. Although the power efficiency, I'll prove it separately. But for the timing, let us understand this from this diagram that how we are trying to achieve it. Okay, so this is analytically we will prove that power efficiency is greater. Okay, so that is separate. But theoretically, or from the aspect of the diagram and the process that is involved with SSB, we are assuming that the power efficiency should be increased. Okay, so is there anyone having any doubt with this? Anyone? Please respond. Anyone? All right. All of you agree that this is fine, right?
Yes, sir. Yes, sir.
Okay. All right. So let us move ahead with the power part. Okay, power saving, because that's an important aspect of it. So power saving in SSB. So how we are calculating it? Very simple. So here what we are going to do, we will take the ratio of the unwanted part to that of the total power. So that is the efficiency. So the efficiency is simple as unwanted power. So I would say like this: unwanted power divided by total power. Okay, simply as that. So unwanted power, what are the unwanted power? One is the carrier power, PC. Okay, that is also there, and the this is sideband power, m square by 4. Okay, and if you observe the total power, if you go back, you will find that this was given by an equation 1 plus m square by 2. Okay, so after you substitute everything and you get this thing done, like PC, if you take common and all those things, what you are obtaining is 1 plus m square by 4 divided by 1 plus m square by 2. Okay, and finally we are obtaining half of, please make a note of this, half of 4 plus m square divided by 2 plus m square, like this. Okay, so my efficiency, power efficiency, if I write as a formula over here, so that is given by percentage efficiency, percentage saving, I would say percentage saving, okay, of power, that is given by half of 4 plus m square divided by 2 plus m square, like this. Now, if you observe that when m is equal to 1, which is the maximum or the highest value that of m that we all know that is possible. So if you substitute over here, so half of 4 plus 1 divided by 2 plus 1. Okay, so that is 4 by 4 by 2 half. So like this it will come. Oh, sorry, 4 plus 1 is 5. Sorry, 4 plus 1 is 5. 2 plus 1 is 3. Sorry, yeah. So like this it will come. So this is about, if I go on calculating it, 0.833. So this is around 83.33% of improvement. Now, in the same process, if you observe DSBSC, last day only we had done, it was coming around 67%. This is for DSB I'm talking. So for DSB, it is coming around 67% efficiency, which is further improved to 83% almost. Okay, when we are considering the similar condition. So that is why it is advantageous. So already I told you about the bandwidth efficiency. It is imperative that it will definitely have a bandwidth efficiency because of only one sideband being transmitted. Now we have also proved that for SSB signal, the efficiency is definitely increased. So if I consider the chronological order of it, so it will be something like DSB FC, that is full carrier. Okay, that is less. So if I consider the power saving, okay, if I categorize in this way, so DSB FC, I'm talking about the general AM signal. Okay, so that is less compared to DSB SC, and this is also less to SSB. So this is the order in which we are considering the power saving. Okay, so now we have established the fact that all these are advantage to respect to SSB signal. And we also have observed that it's very easy in a way to generate an SSB signal, because if the DSB signal, if the DSB SC signal is fed through some kind of a band pass filtering, okay, and if I want to tune it to only the upper sideband, then the SSB output will be generated. All right. So what I mean, if I diagram wise, if I show you, so in fact, this is my suppose MT, okay, and this is my cosine wave. So local oscillator is there, local oscillator, which is giving us the AM DSB signal. So AM DSB SC signal. Okay, now this goes to a band pass filter. Band pass filter. Okay, now if I go to band pass filter, at the output it should be an SSB SC with upper sideband only present. Okay, so if you observe carefully that what in the equation wise, if I go, so it is like if DSB SC, so ST is something like AM by 2. This was given from the earlier day, cos of 2 pi FC plus FM into T. So this was the upper sideband plus AM by 2 cos 2 pi FC minus FM into T. Okay, so this was the upper sideband. This was the upper sideband USB, and this was the lower sideband LSB. All right. Now, if I want to go through this band pass filter, like I have described over here, band pass filter. So your SSB should only have either AM by 2 cos 2 pi FC plus FM T or FC minus FM T. So this is the structure that we are observing. All right. So this, in fact, this method that we have discussed over here, just a very simple, it looks very simple. This method is called as, please make a note, frequency discrimination method. Okay, discrimination. Okay, discrimination method. Frequency discrimination method. This process that I told you right now, that we have a DSB SC signal, we will just put it through a band pass filter and we will generate an SSB signal. So this actually is called as frequency discrimination method. But the process, although it looks very simple, there is a major problem that comes in with this. Okay, what is the problem? Just understand this very carefully. Okay, let me first draw a diagram and then I'll explain it. Okay, so suppose what is happening over here, you see that we have the same diagram that we already have drawn previously. So suppose this is my minus W, this is plus W. Consider it to be the if you can consider it and in terms of FC FM also, no problem. But anyway, so this is the frequency. So XF, suppose this is my X of F. This is my W axis, suppose frequency axis. Now after the DSB that we are getting through, so it is coming something like this. Okay, already I have drawn this previously. Still maybe for our reference as well. All right, so this is the thing. Now if I happens to write it the specification, so this point is FC minus FM. This is minus FC plus FM. This is minus FC. This is plus FC. This is FC plus FM, and this is FC minus FM. So these are the categories. Okay. Now, the problem that comes in, you forget about the left-hand side. You forget about this red color left-hand side portion. Leave it. Okay, don't look at this. Just look at the right-hand side. So what we are trying to do is that in case of our principle that using a filter, we are sending, suppose this shaded portion. Remember, this shaded portion is the USB portion. All right. Now, if I look at these 2 points, just I'm mentioning these 2 points somewhere over here. Sorry, somewhere over here maybe, and some point over here. Okay, and I mark this point as A for our reference and mark this point as B for our reference. Now, if you closely observe this A and B, there is a very problematic scenario that occur. Why? Because you can see that at this point A, which is very close to this FC and this boundary, this is the highest frequency of the LSB. So if I just happens to write it down so that the words are, words are important. So at this A point, okay, this is the highest frequency of the LSB. Got it? Because this part is nothing but the LSB. Okay, so the last point, so A is suppose lie right at the corner. Okay, I'm just for illustration, I have given it a little gap over here. So this is the highest frequency of the LSB, whereas this B is the lowest frequency of the USB. Right? So if you are having that kind of a small separation, the term is like that only. I'll just write it down again. So if you have a very small separation, okay, between A and B, okay, which is happening at this point at least, then we'll have to have a very high cutoff filter that will recognize these small overlapping frequencies at ease. Again, I'm repeating it once again. What I need, if there is small separation, then we need a high cutoff filter. If you remember, I told you already that basically filter is nothing but it will segregate. It will allow some portion to go through and it will cut off the rest of the segment. But here what we are assuming that since A and B are very close to each other, if I need to segregate amongst yourself, okay, we need a very high cutoff filter. You can imagine the scenario as I usually give an example to it, like suppose the World Cup final of cricket that happened last year when New Zealand and England were all tied up and everything. Then the last thing that came into picture was the total number of boundaries scored, and based on that, England was declared the winner. So that is basically the high cutoff filter. You need so much of a filtering to segregate the two things out. But truly speaking, while you're doing an electronic engineering and you're doing an electronics circuit design, this high cutoff filter designing is very difficult. Because for this high cutoff filter, you will need a crystal resonator. No need to understand much because this is not there in your syllabus. So crystal resonator. Okay, and this crystal resonator actually has a Q factor. There is a factor called Q factor. Okay, it's something you can say like it's something like a qualitative factor. Now this Q factor needs to be very high if you want to make it as a high cutoff filter, and that is virtually impossible. All right, so that's why using a single bandpass filter over here, it is not always possible to generate a very good SSB signal. So that is why people have found out that there can be two-stage process where there can be bandpass filter 1, then the signal is passed through bandpass filter 2, and then we gather the input signal or gather the input of signal of SSB at the output. And if you are using multiple bandpass filter, naturally you won't require very stringent requirement, right? You will put some small lesser order filter in those cases. So the design complexity also reduces a little bit. So that is another way of doing it. But this is the most simplest of the process to generate SSB. But since it has this inherent problem of detection part, it is not very favored. All right, so this is about the frequency discrimination method. This is something different to that of existing technique. As of now, whatever we have come across, this technique was not there at all. All right, so that's why it is a something of understanding. So hopefully this is clear to all of you. Please respond me if you have any doubt with this frequency discrimination method. Anyone? Guys, anyone?
No doubts.
Okay, so let us continue with that. So what can be the better method? Okay, the better method which usually is preferred for the time being, and that is called as phase shift method. Okay, so and naturally there are other methods of generating SSB signal, and as I already had told you that I'll be keep on adding up these references. I'll put the word reference 1, 2 like that in the file itself so that it's easy for you to understand. So those files are for extra. Okay, so if you want to go ahead with those extra documents, you can definitely go ahead with it. And if you have doubt, you can ask me, but those are not required for the syllabus. Okay, but this is again it is there in the syllabus. So let me I'll just show you this diagram from the PPT itself because it's a little elaborated diagram. So let me just show you. It is basically the phase shift method. Now, if you observe carefully, this is something very unique that is happening over here. It is very similar to the balance modulator that we had already discussed in the previous segment. So that's why it is relatively known to all of you. So if you observe in the balance modulator for DSB Sc when we did it, it was a 180-degree phase shifter somewhere over here. Okay. Instead, now we have a minus 90-degree phase shift. That's the basic change. Otherwise, the circuits and everything absolutely are the same. So here what we are trying to do, this is the local oscillator carrier, which is generating the carrier, and it is getting 90-degree phase shifted over here as well. You can see VC cos 2 pi FCT is converted to EC sin 2 pi FCT. Okay, this should be EC ideally because EC is the amplitude, so this should be EC actually. Okay. So ideally what is happening that we are multiplying both the product modulator M1 and M2 by a 90-degree phase shifted carrier. Okay, so if I write it quickly that M1, okay, output of the N1, if I consider output of the M1 is somewhere over here, this is given by if I consider XT, so that is this one XT multiplied by cos 2 pi FCT. So multiplied by EC cos 2 pi FCT. All right. And similarly in M2, you can observe that this is EC sin 2 pi FCT, and this gets multiplied by X prime T. This is called as Hilbert transform. Again, something which is beyond the scope of this class. But ideally, when you are shifting a signal XT to minus 90-degree, some property wise there is some change. Okay. So here X bar T is the Hilbert transform of it. For the time being, you just understand and remember it that way. So this is given by X prime T multiplied by EC sin 2 pi FCT. All right, because this is the sine part over here. And naturally, what is happening now, the output is nothing but an adder. Now, why do I need an adder? If I do it adder, we will have USB as the output. Okay, just remember this. If it is minus, if I go for minus, it will be the LSB. But usually we will prefer to have USB always. So most of the cases, this will be adder only. So instead of adder, if you have added a subtractor over here, so the sign would be minus minus. Okay, and in that case, you will get the LSB as the output. So what we are trying to do? We are just adding up these two. Okay, so the adding up process involves EC takes common. We are taking it out. So this is given by XT cos 2 pi FCT plus X prime T sine of 2 pi FCT. So this is basically the component that is generated as the SSB, and this is for the upper sideband. All right, so this is ideally the phase shift method and the process that is involved. The final outcome is the nature of the SSB signal. And in that way, what we are obtaining actually over here, that you can see that in case of phase discrimination method, which is this one, phase shifted method and all, we have a lot of advantage. Okay, you can see that the design part. Okay, in case of frequency discrimination method, there was nothing called as a phase shifter, so it was relatively easier design. But in phase shifted method or the phase discrimination, sometimes this is called as phase discrimination method. The first discrimination, the earlier one was frequency discrimination. So it is if I relate it that way, so phase discrimination method, but here the circuit is complex. Okay, because the design is critical. This phase, if it gets varied by some means, there will be overall error in the circuit. All right, so that is ideally the advantage of this is the way we are doing for phase discrimination method. All right, this is similar to the balance modulator that we had already discussed. So I'm not focusing much on the usage and all. So let me go back to here. So phase shifted method is also done. So these are the two promising methods that we have discussed on the generation part of SSB. Right, now let us quickly move into the last segment, which is the naturally the receiver or the detection of SSB CSCC. Naturally, if you observe that AM in DSBSC, everywhere we have to detect as well. When we are transmitting something, we have to detect as well. So the first thing that, and the most commonest of technique that is usually used for the detection of SSB is called as the coherent detection. The same thing that we had discussed already. So coherent detection. I told you even on that day's class as well, the previous day's class as well, that this coherent detection will be used in some other technique as well. So this is the basic technique. So what should be the coherent technique? Coherent technique should be like if you have an SSB SC input. Okay, so this will be a product modulator. It will be a product modulator. Okay, and here we will have a local oscillator that will generate some kind of a frequency or the carrier frequency FC, which will be exactly tuned. Okay, which will be exactly tuned to the carrier which is there in the transmitter. And this product modulator output should go through some kind of a low pass filter. Okay, low pass filter, because we are generating the modulating signal. Again, remember this modulating signal is always having frequency which is much lesser compared to the carrier signal. So always we will have a low pass filter somewhere over here. All right, so this is the process of coherent detection. It was same in the previous diagram as well. So nothing new over here. So the input is SSBSC. That's the only change. So you're generating using a phase discrimination or a frequency discrimination method, and you are generating that SSB. Now you are sending that over the antenna and you are receiving it. So now the SSB signal goes to this process. Now the output, if you observe that carefully, if I go by the output, so ST, if I consider that is the output, okay. So ST is half of EC XT cos of 2 pi FCT plus minus X prime T cos of, okay, it was sine over here, I guess. Okay, it was there in that file. Anyway, so that was sine 2 pi FCT back there. So I would write it as, okay, since it's minus, so we can write it as cos of 2 pi FCT as well. So that's how the SSB signal would look like. Okay. Now this is since we are adding a plus minus, we can have this cos in fact. All right. So now if I multiply this ST, that is the input over here. This is ST actually. Okay, by a FC, that is the cos 2 pi FC. Okay, cos 2 pi FCT. So whole thing multiplied by cos 2 pi FCT. If I multiply this, so you can observe that there will be a scenario where there will be cos 2 pi. So there will be something like half of EC XT cos of 2 pi FCT multiplied by again cos of 2 pi FCT. Okay, plus minus half of EC X prime T cos 2 pi FCT. Okay, and we have and okay, this should be sine actually. I was correct. In fact, this should be sine. Okay, just change a little bit. This should be sine. Yeah, cos 2 pi fct and sine 2 pi fct. Okay, so these are the final outcome. This is nothing but st multiplied by this. Now here you can see there are two things that is coming. One is called as this term, and the other term is this one. Okay, so a and b. So if you remember the trigonometric identity, so cos a multiplied by cos b. If you check this one, this should be usually half of cos of a plus b plus cos of a minus b. So the same thing is applied over here as well. You can see here a and b are the same. Okay, a and b and the same. So this part is coming as half of ec xt. Okay, cos of 4 pi fct. Okay, plus cos of 0 in fact. So this is coming like this. Okay, and there will be a half over here. So this will become 1/4. So this is for the first part. This part. Okay, and plus minus if I consider half, again a 1/4 will come in ec x prime t. So cos a sine b. So this is equal to sine a plus sine a plus b. So this will be like sine of a plus b. So 4 pi fct and plus sine of 0. So this is the trigonometric identity. Now cos 0, as you can observe that we can have sine 0 as 0. So this is done. All right. So we will only have that. So the final outcome we should be 1/4 ec xt plus 1/4 ec xt cos 4 pi fct, and the final term is plus minus ec by 4 x prime t sine of 4 pi fct. Okay, so these are the final outcome that we are getting. Very simply, you can find it out from your understanding. So these are the option we are getting. Okay, now you can observe that what we are getting is that very interesting result is that if you look at closely this first term, okay, this is nothing but a scaled version of xt, which is nothing but the message signal. So this is equal to the message signal. And the rest of the portion that you're looking at over here, they can be unwanted terms, unwanted, and this is for this to remove, you need the low pass filter to remove it. So the final outcome of S of t would be nothing but 1/4 ec xt as the outcome. Clear? So it's very simple. In fact, it's not that difficult, and the calculations are also detailed given in the course page. So what we observe is that using this technique, using the coherent detection, we can finally get a very nice easy way of finding out the message signal from the mixed signal of SSB. All right, so that is basically the coherent detection. But again, as discussed in DSB, here also we will have issues with respect to the coherent detection, because here also you are generating a carrier frequency which should be, we are assuming that is, it should be same as that of the transmitted carrier. And naturally, there will be some kind of a phase distortion. If it happens, then the same kind of a frequency phase error like it was happening in DSB will again happen in SSB. Okay, so what I mean is, suppose if I consider instead of that carrier frequency which was cos phi ft, so the carrier frequency was cos 2 pi fct. Okay, instead now we are assuming that the frequency has an error, or the phase has a new phase, that is phi. If this is the case and you go on multiplying and do the process again in the same way, your ST would look something like 1/4 ec xt cos of phi. This term will be there, and then plus minus 1/4 ec x prime t sine of phi. So now the phi is a factor based on which xt is varying. Now if you closely observe the same way, if I consider that phi equal to 0, okay, then cos phi equals to 1, okay, and sine phi equals to 0. So if you substitute over here in this particular equation, you can see that at this point, the output of ST will be nothing but 1/4 ECXT. But when phi is equal to 90 degree, again your cos phi will be 0 and sin phi will be 1. Okay, hence you will have ST as 1/4 EC x prime t sine of sorry, this is 1, so x prime t, something like this. Okay, and this is also a transformed output you are getting, negative, like a kind of a transform from xt to whatever you are getting. So again, you have to do a re-transform in that some order. All right, so the point is that if you are using a phase method or this method, in fact, there is always a chance that the phase error or even the frequency error can also happen for the timing. Okay, so that is how the errors will creep in the overall data. So that is why what we usually do is that the SSB signals, no, they are very much suited for the audio signals. Okay, or not audio signal, but voice transmission band, because the voice transmission is around that 600 hertz and all. Like wherever the upper and the lower sideband has a certain period of gap of the frequency, then only it is possible. Otherwise, you need to have very sharp filters, and that is not very, I would say, that is not possible in a way, and that's why SSB is not very much useful as an application for this kind of a ways. Okay, so it is mostly for the for audio signals. For example, audio signal has a frequency band of 40 hertz. Now 40 hertz is the band, audio signal band. So the upper and the lower sideband, you can imagine they will be very, very tightly spaced. So definitely SSB signal won't be, or SSB or suppressed carrier method cannot be applied on an audio signal for that matter. All right, so that is one of the biggest drawback of it. So so this I think should be enough for today. So we have discussed, sorry. So we have discussed the details about the SSB signal, the generation of it, how and why it is so important. And we have also found out the different generation and the modulus detection techniques which are existing. And we have found out the pros and cons of all those techniques one by one, so that we can able to figure out that which one to choose. And coming next day, we are going to finish off this module with a last segment, which is a vestigial sideband. Okay, so that will be some kind of a compromise between the DSBSC and the SSBSC. It will be something in between. Okay, so let us wind up the session. I'll stop recording first. I'll stop recording.